Okay, let's go back to what we have. So we have a population here, and we have a random variable. And we have a sample. The same distribution, and so, well, if we assume that this x is normal with mu and sigma squared, then we found that point estimation gives us gave us that x bar n mu, and we found that the square n So, we have a population and we have defined a random variable on this population, and we want to study that. This random variable can be, say, the age of people in a city, say. The population can be people in that city. Then we have we take a sample of size n, which means that we have n random variables x1 to xn, each one has the same distribution as x, and then we study that random sample of size n. Now let's assume that x is normal with expected value mu, mean mu, and variance sigma squared. We found in point estimation that x bar n, this formula, is an unbiased estimator of mu, and s squared n is an unbiased estimator of sigma squared. And we found the distributions for these, and if you look at this, this is random, so this is random because it's the sum of random variables. And we found distributions for this one and this one, normal and chi-squared and so on. So that was the point estimation. Now, in interval estimation, we go back to these two, and we try to do something else. So we try to find like an interval. In fact, we find these two, and then what are we trying to find? We are trying to not find, say we want to study, or we want to say estimate, or these two in fact, mu and sigma squared. So we come up with some statements that tell us, say for example, where mu lies, or with some probability, mu lies in certain interval, and also for sigma squared. So let me start with mu and tell you how what that interval will be for mu. So let me erase this thing, the premise of the problem. So let's say that x has normal distribution, and we have a sample of size n, x1 up to xn, and using that sample, instances for the sample, we have found x1 up to xn, and then we have found x bar. So let's just write x bar as a random variable. That's 1 over n. Say sigma I from 1 to n xi, and s squared. Let's put n here because this is also an n. I from 1 to n xi minus x bar n squared. Okay. So, now what are we trying to do? We are trying to do this. Let me go back to my notes and so we had this situation. That x bar n minus mu over sigma over square root of n that goes to normal 0, 1, and we use this to do problems on x bar n. So that is a central limit. And we also found that x bar n minus mu over s over square root of n, and this is in fact Sn. That is in fact what we call T distribution with n minus 1 degrees of freedom. So T distribution with n minus 1 degrees of freedom. Now, where does it come from? T distribution is, look at the top, this is normal distribution. What is Sn squared? Sn squared was chi squared, so it's something like this. It's like normal divided by square root of chi squared, something like that. So this, there are some other things here, but basically this thing gives you a T distribution. So, and T distribution is just amazing because I discussed this before. So it is symmetric with respect to, so it's average is 0, say, and as n goes to infinity, the T distribution becomes a normal 0, 1. So T n minus 1 goes to normal 0, 1. And it really looks like normal 0, 1, except for, well, it just changes as n gets larger and larger. So, for n large, we are really getting closer and closer to the other one. In fact, we should, because then this looks like this, and so on. Okay, so. So let's go back to this, and let's call this like Zn. So let's call this Zn, and Zn is x bar n minus mu over S n over the square root of n, and we know that this is T distribution with n minus 1 degrees of freedom, and we want to do this. So we let alpha be a number between 0 and 1. So alpha is can be probability of something because it's a number between 0 and 1. And we consider 1 minus alpha. This is more customary to use this. And we find Z alpha such that the probability of this Zn between Z alpha and minus Z alpha is 1 minus alpha. So let's look at the picture. The picture is much better to look at. So we have Z alpha minus Z alpha here, and Z alpha here, and we want to find this. It's not that hard. It's in fact the inverse. So this, we want this area to be one minus alpha area, which means that this area on the right is alpha over 2. This is alpha over 2, and this area is also alpha over 2. Sometimes this Z alpha is denoted as Z alpha over 2. So if you see that as alpha over 2, maybe it makes more sense, because the area after this is in fact alpha over 2. And you can see why I chose alpha, and then I said 1 minus alpha, because 1 minus alpha is this, and we're dealing with these, say, residues or something. So, so let's say we can find these two. It is not that hard, but as I said, it's like the inverse of that t. Any calculator has this function. And so suppose we found the Z alphas, and now let's plug in this thing for Zn and see what happens. So let me erase this picture and go back to this. And so we have found Z alpha such that minus the alpha less than this guy here, x bar n minus mu over Sn over square root of n is less than Z alpha. Less than Z alpha is equal to 1 minus alpha. So this is equivalent to this. If I multiply by this, because Sn is not 0, so if I multiply by Sn over square root of n, I will get this, and that's the same thing. Minus Z alpha Sn over square root of n less than x root of n minus mu, and this will be Z alpha Sn over square root of n, and this is again 1 minus alpha. So if you see this is all the same. So if I multiply all three sides, all of them by -1, if I do that, this is what happens. I will get mu minus x bar n, and you see they are flipped. So this flips this way, this one flips this way, and if I just flip the whole thing, I will get the same thing. And on this side the same thing, minus Z alpha Sn over square root of n. So now if I move x bar n here and here, I will get this nice statement. So this guy here is equivalent to this. So let me write it here. Just some simple algebraic manipulation will give me this. X bar n minus Z alpha Sn over square root of n is less than mu less than x bar n minus Z alpha Sn over square root of n. Or if I write it in say interval notation, this is telling me that the property that mu belongs to this interval x bar n minus Z alpha Sn over square root of n, comma x bar n, oh this is plus Z alpha Sn over square root of n is 1 minus. I need an extra bracket. So Now this is what we call a confidence interval. So this is called, well, let me write somewhere up here what this thing is. So let me erase this, and so the interval so the interval x bar n minus z alpha s n over square root of n comma x bar n plus z alpha s n over square root of n is a 1 minus alpha times 100 confidence interval mu. Well, finding confidence interval is not that hard. So how do you do this? So you basically do this. So you have a population and a random variable here. So take a sample of size n. So 1, 2, find or calculate x bar n and s squared n or sn 3, and what is given to you? So given alpha, and what are usual values? Alpha can be any number between 0 and 1, but most often you are given this. Most often alpha is 0.05 or 0.01. Okay, so that first one will be 95% confidence interval, 1 minus alpha will be 95, and the other one is 99% confidence interval. So given those two, but it can be a number, any number between 0 and 1. 3, find using Tn minus 1, find z alpha such that probability that Zn is bigger than z alpha is alpha over 2. Okay? Remember the two sides were alpha over 2. Then, where should I write this thing? So let me erase this. So when you find the alpha, then, well, that's in fact written here, so 4. Then, this thing is okay, finished. So, yeah, so this was already written here. Okay, so your job, given some data to you, or if you find data yourself, is simply finding x bar n and sn or s squared n, and then finding that z alpha, which is not that hard, and then that's it. Then this is your confidence interval, and well, some people like to say that. I'm saying 95% confident that mu lies in this interval and things like that. Well, you know, you can say that, that's okay. But what is this in fact? What have we, so what is this, the probability that I note? So let me write it again and discuss it more carefully. So let me erase this thing. So we had this situation that I wrote something like this, that the probability that mu belongs to this interval. Now this is a statement. This is a random interval. It's interesting. This is a random interval. It's a random interval. And what does it mean? It means that the two endpoints are random, right? So the two endpoints are random. In fact, when the two endpoints are random, in fact, when you have them, they determine other points between them. But anyway, the two endpoints are random, and you can see why they are random. And remember, the x bar n and Sn are, in fact, random variables, and we found distributions for them. So this interval is random. So when I say probability of something, in fact, this is a statement about this random variable, right? And that's in fact true. This is a statement about x bar n and Sn. And one can say that this is the statement that is related to the joint distribution of x bar n and Sn. So, like what? Like you might say, okay, what am I talking about? Let me give you an example of this thing. So, if I have two random variables, if say we have x there, so let's say if a and b are random variables with joint PDF, say f of say AB, then C equals, maybe let's write a minus b is a random variable, and is a random variable which is related to these two and related to this joint PDF. So something like this, if I said p of a minus b less than mu, for example, and you can see that mu was between this and this. So on one side is like this. So if I say something like this, this is a statement on A and B. It is a statement on A and B. And related to the joint random variable. So related to the joint distribution. Joint distribution. Okay. So it is somehow important to realize what we are doing, or at least to realize that this interval is random. So when you do an experiment and you find this random, these numbers, and you come up with an interval, that is your interval. That's what you have found. But that's what that team of, say, research scientists or whatever have found. In fact, that team that sample x1 up to xn, that team has found in one experiment. So it changes. If you do it again, if the team does it again, the team might find another one, and does it again and again and again, you can find more and more. So what's going on? And that's interesting that for any one of them, you can say this. You can, for any one of them, you can say that this mu, in fact, the probability that mu lies in this is 1 minus alpha. So what's going on? You have a situation like this, that if this is say the axis, like the x-axis or whatever, right? The x-axis, and mu is here. Mu doesn't change. Say if mu is, for example, if you are studying the income of people living in, say, a city, say Minneapolis, for example, then it's well defined. So you know people who live in Minneapolis, and you can, if they let you, let's assume they let you know that. So you can find the income of each one of them per year from, say, IRS, for example, or some other place, and then you can come up with this interval. You can come up with this mu. So you can find that mu. So let's assume you can find this mu. So this mu is in a sense fixed. And so this is like a point on x-axis. Now suppose you cannot do that. Suppose they won't let you, or something happens, then you have to go with some, you have to do sampling. So you find a sample of n, and ask them their income, and they give you numbers, and then you come up with a random interval. And your random interval might look like this. So this is your random interval 1. Another team might find this random interval. Another team might find this random interval. Another team might find this random interval. Then someone might find this random interval, and so on. So each one of them is a random interval found by some team, or maybe the same team does it again and again. And what I'm saying is that, what this statement is saying, that whatever number of times you do this, the probability that this mu falls within this random interval is 1 minus alpha. It's probability statement, right? So it's not saying it will fall. Will means what? Probability 100%. There is no 100%. So, and you can see maybe this happens. Maybe it's not within this. So, in a sense, it's saying that if for example, alpha is, say, if alpha is 0.05, then 1 minus alpha is 0.95. It means that if you do this experiment 100 times, so if you do this experiment 100 times, you expect that mu falls within the interval that you find each time 95 times. So let's say 95 times average. In average, 95 times out of 100 times that you do the experiment, you expect this mu to fall within the interval that you find. So that's the meaning of this. It also should remind you of something else, that it looks like that each time that we do an experiment, there is a chance of failure. It is there, that alpha is a chance of failure, so there's a probability of failure, which means there's a probability of success here. So it is, in fact, each time that you do this, it's like a Bernoulli trial. So this falling within this interval is like a Bernoulli trial. So there's a success and failure for that. Success is this falling within this interval. Failure is this not falling within this interval. So what we are saying is that if falling within that interval is success, the probability of success is what? P of success is 0.95. And that's a good probability, right? That's amazing. So, and that gives you a much better perspective to what is going on. So we are dealing with uncertainty. So in my opinion, this is a lot, it's much more closer to say uncertainty that is, these problems have, than saying, okay, we found x bar n and we think that x bar n represents mu, and in fact taking that to be your mu. Many say statisticians, or those even places that do statistics, like that website 538, they prefer this. They say, I mean, if you look at statistics they give you, most often even you might say things like this. So in fact, this is a much better, say, approximation, because what you are doing is uncertain. You're in the uncertain world. So this makes a lot more sense than just putting your finger on something and say, yeah, that's it, that is the average. Okay, now, one place that I saw this thing happening is, and another thing, when you have, and you will see that, because you see, if this is, if you just, so this is 0 and this is, say, tn minus 1, and z of, say, this is z of alpha, that's 0.05, and I said this, sometimes people write it alpha over 2, so that's 0.025. So if that is z for 0.025, then z for the other one, z for, say, this is z for 0.01, is to the right of this, right? So this is z of 0.05 is less than z for 0.01. So 0.01, alpha 0.01, will give me a larger interval. You see, this z is here. If I have a larger number here, with the same x bar n, Sn, and square root of n, if this z alpha gets larger, then this endpoint gets to the right, goes to the right, and this endpoint goes to the left. So if an interval looks like this for z, for alpha equals 0.05, then for alpha equals this one will be for alpha equals 0.01. Which means the interval for alpha equals 0.01 is much larger than the interval for alpha equals 0.05. If we use the same data. If you use the same data, then this is what happens. Now, so if you need more, in a sense, confidence, then your interval is much larger. It becomes larger. Now, I have seen, as I said, I have seen some medical devices, like the one that I have seen is, let me erase this. What I have seen is on blood sugar tests. So the blood sugar test is like a device, something, say, and it reads the blood sugar, and then there's a stripe like this that goes inside, and the stripe has some area here that the blood goes here in this area, and then when you insert this into this, it reads the amount of sugar on this small portion, and then tells you that your blood sugar is 95. Well, I don't care what that 95 means, okay? Now, when you buy something like this, I have seen that. There was one Chinese one, and it said, okay, you have to somehow check your device and see if your device is working correctly. So, and it usually comes with like a test fluid. Now the test fluid is what I think it is in fact like some sugar, some sugar dissolved in something, water maybe, or it might be something else, I don't know. But it definitely has the certain amount of sugar, exact. So this test sugar has certain amount of sugar. Known amount of sugar. Okay. Now what they do is they say this. Okay, put this test fluid. So put this test fluid here and insert and check the reading. And if the reading is, say, between 95 to 150, say, then your device is working properly, correctly. When I saw this in the brochure of that, I was just going nuts. Say, wow, I'm not sure that it was 95 to 150, but the difference between these two was about 75 points, something like that. So, and people who don't know what this thing is, they just don't care, and they just insert and see, okay, the reading is like 100 and say 5, and they say it's okay, because it's between these two. What they're doing is, that is in fact confidence interval. So what they have done in factory, they have checked like 100 of them, 100 of these devices, and they have found a confidence interval for, so suppose they have, I'm not saying 100, I mean N. So they have checked N devices, say, N devices at random, and they have found X bar N and S N squared. This is the X bar N of the reading, and this is S squared N of the reading on the device. Then using this, they have found that 95 to 150. Now, I didn't see the confidence level, so that alpha sometimes is called confidence level, or they say at level alpha, or 1 minus alpha times 100, something like that. But I didn't see that level, or I can't remember if there was any level written. So now, so that's it. So the company that has made this device is telling you that that's it. So if it falls within this interval, then your device is working correctly. Now, if this stripe is, for this one, the stripe was like this big, say. I'm not saying exactly this big, no, it might be, it's much, much smaller. So I'm just comparing. So if that was this, then there was another device, and the stripe was like this. So this one has this much area, this one has this much area. So this is the one device, free device, and free stripes. In fact, insurance pays. This one, no. This one, the stripe is not free. No, not free. In fact, if you somebody you could buy this without insurance, and I, in fact, asked the pharmacist how much that is, and that was a long time ago, and I remember it was in the hundreds. I mean, I was just going, wow. So I didn't buy it, in fact, but I couldn't do that. But anyway, now the confidence interval for this one could have been, I didn't check, but it could have been much, much smaller. It could have been like, say, 95 to, say, 110. This was like 95 to 150. And no wonder the second one is not free. The insurance company doesn't pay, even doesn't let you buy that. They say, no, that's too expensive. They won't pay for that. And why? And I think the insurance company is just playing with human health, because this device, which has this confidence interval, which it was even more than that, 75 points. And 75 points is a lot. And so if the reading could have been to the end of that, so when you just put it and you check your blood sugar is like 160, and you say, gee, I'm dying. It shouldn't be above 100. 160 is like I'm dying here. So, wow, I mean, it was crazy, but anyway, the point was not that the device was bad, but it was the confidence interval which was interesting. Interesting to me that the device had such a large confidence interval for about 75 points. And I talked about another company the other day that, in fact, this company, which was again a medical device, and they were claiming that they were doing it. They made the devices. Walgreens and some other pharmacies, they bought it. They were selling it. So the device or the stripe, for example, that was checking was this big, while the device should be like this big to make such prediction. When you give blood for certain, say when you go for a blood test, they take this amount of blood. It's a lot more than just this tiny minute drop. So for this tiny minute drop, this is the confidence interval. For this much that you give for a blood test, then the confidence interval goes down, way down, because you have a large sample. So, and you can see that this n, as then n gets larger and larger and larger, you will definitely get closer and much better reading and much better confidence interval. So, in fact, that's what happens, and in my opinion, every say medical device should somehow, like this one, well, at least they have given the confidence interval, should really give that confidence interval if it's reading something. If it's reading like blood sugar or say, I don't know, like blood pressure. Now, and you can see how things can go wrong when I was discussing for the COVID-19 test, I was discussing the false negatives and false positives. That's what happens. So if the device that is checking it has in fact such a confidence interval, then, and if you say if something is like the blood sugar, they say if the blood sugar is above 100, then you should be concerned. Or not 100, let's say 120. And you check your blood sugar with this device, it's 160. And say, wow, I'm dying. So that can be some, I don't know how that device checks COVID-19, but it might do something like that. If some reading is above certain number, then they say, okay, you have it. Or if it is not above certain number, then they say you don't have it, right? It's like blood, it's like body temperature, right? Say higher than 100, say, is you should be concerned, you might have it. So it's something like that. So if thermometer is checking your body temperature and it's like 120, then you're basically dying. Or you're dead. So anyway, so that is the story of confidence interval, and also I should emphasize that, as I said, every time you find this confidence interval, you're in fact performing a Bernoulli trial. So each one of them is like a Bernoulli trial, and you have a probability of success. The probability of success is 1 minus alpha, and probability of failure is alpha, in fact. So, and you can talk about what? You can talk about, doing this experiment, performing it, say, 25 times, 30 times or something, and asking the question that what is the probability that out of 30 times that you perform the experiment, the mu falls within the confidence interval. Say not how many. You can ask a question like, what's the probability that it falls within the confidence interval, say 25 times, 26 times, 2 times, or something like that. So you can find those probabilities based on binomial, in fact. So, Bernoulli, when you do Bernoulli's, successive Bernoulli's, you are in fact performing a binomial. Okay, so that was the story of confidence intervals, and and it's good to have confidence intervals on every, say, medical instrument. So, okay, so let me stop this thing and see you next time.